So we can define a recurrence relation for this particular tree generation process or graph generation process that matches the recursive structure of the generating routine. We have a graph with one node, it's going to have 0 edges by the way that this generation process happens. If we have a graph with n nodes, what is it going to do? It's going to call the recursive generation process with n over 2 to generate however many edges it generates with that, and it's going to do that twice, so it's 2 times that. And then at the end, it's going to draw one extra edge to connect the two components together. So this now is a recurrence relation for the number of edges. Now, we know already what this is going to be. There's going to be n minus 1 edges in a tree with n nodes. Let's go through this process anyway of solving a recurrence relation because this is going to be a useful tool. So you can think of what happens as this process unfolds is that to generate a graph with n nodes, it first breaks that subproblem into two things where we work out the number of edges in a graph with n over 2 nodes, but doing that requires working it out for n over 4 nodes, and so on. This goes on and on and on until we get down to a whole bunch of individual graphs, each of which has one node. That's where the recursion bottoms out. Two useful questions. First question is, how deep is this tree that's being built here that bottoms out over here with the ones, and how many leaves is it going to have? So why don't you fill that in? Is the depth that we get this way log n, or 2 to the n, and are the number of leaves at the bottom log n, or 2 to the n?